Hey everybody, this is Miss Eisencraft with Unit 3, Lesson 11, Practice Problems. So let's go ahead and get going. Over here. All right. So first one, it says, what is the length of segment AB? All right, so we know that since these A prime, B prime is parallel to AB, that it will cut these pieces proportionally, and also small triangle to big triangle will be proportional. So when it says what is the length of segment AB, this is part of the big triangle, right? There's the big triangle, wah, wah, wah. And then there's the little triangle right here. All right, so what is the length of segment AB? That's part of the green. So we know that 5 little triangle, so 5 over this AB. So 5 over AB. 5 over AB, right? 5 over AB. Little is too big. As let's find another pair of corresponding sides we know. Little 6 is to 9, because this right here, the big triangle, is 9 units long along the side here, as 6 is to 9. Okay, I'm going to use cross products. So I'm going to go, I know the cross products have to be equal, so I'm going to go 9 times 5 is 45. That has to equal 6 times whatever this is, 6 times AB, which is your unknown, right? So really, you're just taking the 45 divided by 6. And you're going to get 45 divided by 6 is 7.5. That looks reasonable. So AB is 7.5. Okay, 5 is to 7.5 as 6 is to 9. Okay, next, what is the length of segment B prime? Well, I know that not only do these parallel lines cut, small triangle to big triangle proportionally, but the pieces end up being proportional. And see how this is 3 and this is 6? This is going to be half of this. This will also be half of 7. So this is just going to be 3.5. I could double check using proportions that 7 over 10.5 is the same as 6 over 9, and it is. Okay. Number 2, explain how you know that DE is not parallel to BC. Well, if they are parallel, they will cut these pieces into proportional pieces. And so I can see that 2 over 4 does not equal 5 over 9. Those are not the same proportion. I also can see that 4 over 6, right? 4 over 6, that if this was parallel, should equal 9 over 14. And I could check that by cross products, and I think I'm going to get 56 and 54. Those are not equal either. So not parallel. All right, number 3. In right triangle ABC, big one, AC, the whole side is 4, and BC is 5. The new triangle is formed by connecting the midpoints. Okay, so what is the area of ABC? Well, if you remember, a triangle's area formula is base times height cut in half, or times 1 half, or divided by 2. So it's just going to be 5 times 4 cut in half. 5 times 4 is 20. Half of 20 is 10. So 10 square units would be the area of all of this. Okay? So they're saying, well, what about this little guy? DEC, what would his area be? Well, let's first of all find the little side. Since it's the midpoint, we know this has to be 2.5 and this has to be 2. So let's apply the same formula. 2 times 2.5, and then let's cut that in half. Okay? And that's going to be 5 cut in half, which is 2.5 square units. Okay, so this is this little guy. And they're asking, is this half of this? Does the scale factor apply to area? And actually it doesn't, because it applies to the side lengths. And since we took half of this side length and half of this, and then we multiplied half times a half, This became 1/4 of this. So the scale factor for the side lengths apply to the area? No. The area of small triangle is 1/4 area of bigger. And that's because you took a half of each side and then you multiplied a half times a half the side times half the side. So it was 1/4 of the size. Weird. Okay. Next one, number 4. Okay. Which of these is true? To know whether two triangles are similar, it is enough to know the measure of one angle. That is not enough, because then the other combinations, we need to know at least 2 of them for similarity, and that's not enough information. To know whether two triangles are similar, it is enough to know the length of one side. Absolutely not. You can make a lot of different triangles that are not similar. To know whether two triangles are similar, it is enough to know the measure of 2 angles. Yes, that's the angle-angle similarity theorem. Angle-angle triangle similarity theorem. And to know whether 2 triangles are similar, it is enough to know the measures of 2 sides. That's not enough. That wouldn't lock in 2 angles. Okay. All right. Are triangles A, B, C, and D, E, F similar? So first of all, you might notice that they put the shorter side there and the long. I don't know if that was on purpose, but we're just going to use the numbers as they are, even though it looks like these should be flip-flopped. It's fine. Are triangles A, B, C, and D, E, F similar? So we have to have all 3 angles equal each other. This is 100, and then this is 60, and that's 20. Well, if you know 2 of the 3 angles, you can find the third. So 60 plus, using the triangle sum theorem, 60 plus 20 is 80. That leaves 100 degrees left over for that. Okay. And then 160 leaves 20 degrees, because we know any triangle has to have 180 degrees total. So now we can see they're similar because we have 120, 120, or 60 and 20, 60 and 20. Okay. So if possible, so are they similar? Yes. We have 2 corresponding congruent angles. We need to kind of figure that out, though. Okay, so now is it possible to find EF? Again, we're just using the numbers they gave us here, even though they don't look right. It's not drawn to scale. EF is the longest side. It's the side length that connects the 100 degrees to the 20. So that would correspond with this side here. Okay. And then this one corresponds to this one here. Okay. So we could set up a proportion, right? 9 is to 12 as 6 is to what? So we could say 9 is to 12. 9 is to 12 as 6 is to what? We call it EF. So we're really just trying to find this spot right there. Okay. So we can use cross products. 12 times 6 is 72. And that has to equal 9 times EF. Okay, so you really just end up multiplying these and dividing by that third number, which EF equals 8. And I know the picture doesn't look like it. I don't know if it's a typo or they just wanted you to really, but based on the numbers and what it shows, this should be 8. A couple more. Doing great. All right. Number 6. What is the length of DF? This looks very similar to a problem we did in class. DF is right here. It is the side length connecting the 68 to the 28 degrees. Okay. And it looks like this right here connects this, or sorry, corresponds to this one here. Okay. So we can say green is to green as red is to red. Or we can go from the bigger one. Red is to red as green is to green. So this is what we don't know, DF. So we can write, I'll go from little to big. 2 is to 8. 2 is to 8 as 4 is to E. Sorry, DF. So really, right? 4 is to DF. So sometimes you can mentally do them, right? You can just say, oh, this is times 4, so this needs to be times 4. That should be 16. You can go, oh, this is doubled across, so that needs to be doubled across, 16. Or you could do cross products. 32 divided by 2 is 16. Anyway, yeah, do it. DF equals 16. All right, last one. The triangle ABC is taken to triangle A prime, B prime, C prime by a dilation. Select all of the scale factors for the dilation that would result in an image that was smaller. So if the scale factor, we often call that K, right? If the number you're multiplying by is less than 1, it's going to result in a smaller copy. Okay? So we think about, you have to understand which fractions are less than 1. So a half, right? Definitely less than 1. That's going to result in a smaller image. 8/9 is also less than 1, very close to the size. 1 would be an exact copy, and we want it smaller. Nope. Don't be tricked by 3/2. It's a fraction, but 3/2 is really 1.5, so it's going to be bigger. It's going to be over here somewhere. And 2 would result in an image that all the side lengths get doubled. There you go. Hope that was helpful.